Hello, as you know, my name is Nathalie Ziehl, and I'm here to present progress on the search for axions with the nEDM and N2EDM experiments at PSI. So we're looking for axions in the mass range between 10 to the minus 22 and 10 to the minus 17 electron volts. That might seem unusual, but these mass ranges have, they do solve some cosmological problems. Chiefly, they help solve the small structure formation problem. The other reason why we look for these mass ranges in particular is, well, because our experiment is sensitive to them, so might as well. We are interested in the fact that axions interact with standard model particles through gluon coupling. So if we get an oscillating dark matter axion field, then, and we would get an oscillating theta term, that would directly translate to an oscillating neutron electric dipole moment. So we look for the neutron electric dipole moment, and how do we do that? Basically, if we have polarized... Oh, sure. Thank you. If we have polarized neutrons in a magnetic field, there will be an energy splitting, as you know. And now, if the neutron electric dipole moment is non-zero, then we will also get a splitting, an extra splitting if we apply an electric field on top of that. We want to measure this energy splitting by measuring a shift in the Lama precession frequency. So it's pretty much a standard NMR experiment. Oh, right, that doesn't work then. Right, to measure this, we rely on using ultra-cold neutrons. These are special neutrons in the sense that they have a very low kinetic energy. And that means that their kinetic energy is below the Fermi potential of many ordinary materials. So that has the advantage of us that these neutrons will reflect at pretty much any angle on relatively normal surfaces. So we can just store them in special macroscopic containers, just like you would an ideal gas. Right. These neutrons then enter the experiment and are stored in the precession chamber, where they are being kept for the entirety of the experiment. Around this precession chamber, we have high voltage electrodes that generate the electric field. Around here, we have coils that generate the magnetic field. We have magnetometers to monitor the magnetic field gradient here, and we have a mercury co-magnetometer that measures the Lama precession frequency of mercury atoms that are additionally suspended inside the precession chamber. Sorry. Now, a measurement then looks as follows. We start with a bunch of polarized neutrons with spin up and spin down. Then we apply an electromagnetic pulse designed to flip these spins into the XY plane, where they're left to precess for 180 seconds. After that, we apply a second pulse and flip them back again to the Z-axis, where we can measure the amplitude. We're interested in the asymmetry between spin up and spin down neutrons. And the asymmetry, as you can see here, depends on the pulse, the initial flip pulse. It also depends on the Lama frequency. So by doing this Ramsey measurement, we can directly recover the precession frequency. So now we have the data for the nEDM, and we want to look for an oscillation in the electric dipole moment. So normally, if we just look for a frequency, we would just apply a Fourier transform and see if any peaks pop up, but we can't do this in this case because we have very unevenly spaced data points. So what we do instead is we do a least square spectral analysis, or you also hear me talk a lot about periodograms, which is essentially the same thing. The idea is to flip a trigonometric function, like so, to the data, and then we can obtain the power spectrum from the A and B fit parameters. You can repeat this for all frequencies that we're interested in. In practice, this looks like this. We start out with a bunch of random data points, really, and we can weave in an oscillation into this data. And when we then calculate the periodogram of this data, we get something like that. And you can see here the signal that we weaved in shows up at the peak as a peak in the periodogram, which is nice. But also, you might have noticed this weirdo here. So this is, of course, not a signal because we didn't weave it in, but it still appears and it still looks suspicious. And that's a problem. Periodograms are noisy. These types of peaks might appear due to random fluctuations or even due to due to the structure of the sampling of the data points, basically. And that means that the highest peak that we get may not actually be a signal. It also means that the signal may not actually be the highest peak. So this is a problem for us. And how can we solve this? Well, we can start by asking ourselves the question, if we have the nEDM data without underlying axion signal, how would that even look like? What can we expect? And to do that, we can just do a bunch of simulations of periodograms without underlying signals. Then we calculate the cumulative distribution function of this thing. And the CDF then gives us a way of estimating whether a peak that we observe is actually a signal or whether it's just a random fluctuation. However, there's another problem with this. Because we work with lots and lots of data, there's just, very rare events will just happen at some point. So if at some point we have an increasing probability that a very rare event will happen, so that even if we see a peak that, according to our cumulative distribution function, has a high probability of being a signal, there is just some chance that it's not. And the more data we have, the higher this probability becomes. This is just part of how the analysis works, and we have to keep that in mind. We can mitigate that factor a bit by just raising the threshold for our detection. Now, when we looked at the signal, we found, of course, that there was no statistically significant signal consistent with the hypothesis. So we went on to determine the exclusion zones. We did that much the same way as with the null hypothesis. We did a bunch of simulations, this time with an underlying signal with some parameters for the amplitude and the frequency. Then we calculated the CDF for everything. And then we got a 2D plot of parameters where we're sure with a 95% confidence that if there was an axion signal, we would have detected it. And here we have to pay attention to the fact that we're not equally sensitive to all frequencies that we look at. So we have to correct for that by using the CLS method and divide by the probability of the null hypothesis being true. Now, for those of you who've been here a long time ago, these results may be old news, unfortunately. The results have been plotted here. At the time, there were two experiments, two nEDM experiments performing this analysis. There was one at ILL that did the long time base analysis on the data, and the blue one at PSI, as you can see here. Since then, the team at PSI worked on improving these results through better analysis. And the main feature that we included was a change of how we fitted the data. Basically, if we have an axion signal, then part of the data we take for that is with E and B fields aligned, and part of it is with them being anti-parallel. And previously we fitted this data separately from this data, which was not so clever. We decided to do just one fit together, and it gives us a way better exclusion at low frequencies. The results you can see here, we have the oscillation amplitude as a function of the frequency. There is the 1 to 5 sigma levels, and in green is the analysis. So you can see that there is no peak that really reaches a level where it can claim detection. If you're wondering what this bump here is, this is just due to the way we took the data. So the 112 cycles in which we took the data show up as an artifact in the in-phase space. The updated exclusion you can see here, the green data, the green line is still with the data from PSI, but this time with the adapted analysis. And the advantages here are twofold. First of all, we get a slight improve in sensitivity overall, especially here where the blue and red line cross. And the other advantage is, of course, we can achieve this with doing just one analysis instead of two, so we are also more efficient. The big exclusion plot is updated like this. Yeah, the log-log scale make it not look like much, but yeah. Finally, some of you may be aware that we're already constructing a new EDM experiment at PSI, which is supposed to start data taking next year, if all goes well. And there is lots of improvement throughout the experiment. But the most important for axions is probably the fact that now there's 2 chambers. You can see here there's one above and one below. And now instead of having to switch the magnetic field back and forth, we just have one chamber where the electric and magnetic fields are aligned and one where they're anti-parallel. So we can take twice as much data, basically. We also have an improved magnetometry system. We used to monitor the gradient field in the chamber with suboptimal magnetometers, really, that were susceptible to drifts over time. And with the new system, we've corrected for that. So we should get a way more reliable measurement of our magnetic field gradient. Also, just in general, we get better statistics from this experiment because it's, well, bigger, for one. The precession chamber is much bigger. That means more neutrons. That means better statistics. Also, we have now a dynamic magnetic shield around the whole structure that protects us from slowly varying magnetic fields. We did not have that before. And there's lots of other improvements, really. And since we need the data for the neutron EDM to determine the axion signal, it stands to reason that better sensitivity for the nEDM directly translates to a better sensitivity for axions. And with all the improvements in place, we expect about a factor of 10 overall improvement for axion detection. This already concludes my talk. Can't go on. I thank you for your attention, and
First question. Thank you very much for the nice talk. Also, but I would make a strong strong proposal not to present the results from the search of looking for axion-like matter via the oscillating neutron electric dipole moments in terms of a plot coupling to the gluon versus the mass, because theoretically this does not make so much sense, because if you assume just an axion-like particle which has a prescribed coupling to the gluon, then its mass and nothing else, then its mass is predicted by mixing with the pion. And so it must lie on it, then it's the axion. And for an axion, if you just say that's the axion-like particle, then you should plot the coupling to the end, to the neutron electric dipole moment versus the mass. This is fine. I mean, you can, but the other one needs an assumption. Then you have, because we have to add further terms to the low energy effective Lagrangian, which cancel the mass distribution from the mixing with the pion in order to leave this line of electricity axion. So it's just so we have removed this such a block, or we did not put such a block in the particle data room, and what Scherrer makes now a reminder that this kind of plot, coupling of the photons versus the mass, needs to be taken with a grain of salt, just for the theoretical point of view.
Okay, thank you for pointing that out. You've blown my cover. I'm not a theorist.
It's not your.
Okay, that was the electric field in the previous experiment. What will be in the next one?
I don't actually know the exact value of the electric field. I'm sorry.
Okay, and then I have also another quick question. So you take, you have a candidate.
Sorry?
Yeah, so you do your analysis and you have a candidate.
Uh-huh.
After you have taken data.
That would be nice.
Well, you showed one, right? You showed
That was just a simulation. Yeah.
Okay. But if you do see a candidate, how do you process? But it's still sort of marginal in terms of statistics. What do you do?
Well, we would have to take it with a grain of salt. I don't think there is really a reliable way of determining, of differentiating between a signal and just a very, very rare random fluctuation with a confidence level of 100%. So you just have to raise the thresholds and then...
Well, there's a question. So do you raise the threshold for all masses or just for this one where there's a candidate? So how do you do this? Anyway, we can discuss this over coffee. If there are no more urgent questions, we are very on schedule. Let's have some coffee and come back if you're at 11:10. Thank you.